All right, the second example we're going to look at here also has to deal with Bernoulli's equation. So the idea is you have a pipe here, which is oriented at an angle above the horizontal, and what you might be asked is how much larger is the pressure at the bottom of the pipe versus the top of the pipe, right? So what we're looking for here is a change in pressure. Now, to assist us with this, we're told a couple of things. First of all, we're told that at all points in the pipe there's a constant velocity, and we're told what the density of the fluid is. Now, in order for us to do this, again, we have to pick 2 points to deal with here. It doesn't matter which two that you pick, but since we're comparing the top and the bottom of the pipe, those are the best places to pick. So let's pick the original side to be, say, the top of the pipe, and let's choose the prime side here to be the bottom of the pipe. Now, what we want to do here is we want to process all the things that we've been given. First of all, we're told that the fluid in the pipe has a constant velocity. What this means is that these two terms, the two velocity-dependent terms, will cancel one another out because they are the same on both sides. Now, what we're left with here is we're left with two pressure terms and two density terms. And what we want to do here is we want to figure out how much larger is the pressure at the bottom than at the top. So basically what we want to do is we want to group terms that are the same together. We're going to want to bring the red, or the starting pressure, to one side, and we're going to want to bring the gravitational term to the other side. What this does is it changes our equation here into something that we can solve. First of all, we're going to have P minus, or P prime minus P on one of the sides, and this is going to be equal to rho times G times H minus H prime. And this is fine because H minus H prime is going to be positive. Now, once we have this, our goal is to put everything together. First of all, what we're actually asked to find is this difference in pressure that's here on the left-hand side. So that's what we want. We want this together. In fact, what we can probably say is we can probably say that this left-hand side here is delta P. Now, as for the density, we're told what it is, and we're going to leave everything in here in SI units, so our P will be in terms of pressure. Gravity, this G again is just a shorthand for the magnitude of the acceleration due to gravity, which is just 9.8. And then lastly, we need to figure out what the difference in height is, so delta H. This delta H here, again, is just the vertical displacement that we're going through. All right, so if we were to draw this, delta H is simply from here to here. All right, so in order to complete this, what we really need to do is we really want to find this delta H here. Now, we can do so because, again, this is going to make us a right angle triangle with an angle in the corner of 30 degrees, and we have the hypotenuse of 12 here. So what we can do is we can say that sine of 30 degrees is equal to delta H divided by 12 meters. This we can use here. We can solve for delta H. If you do so, again, just make sure to do your trigonometry properly. And what you'll get here is a vertical displacement of 6 meters. The reason why it's positive 6 here is because we've done H prime minus H. Our delta H here is upwards, or positive. So what that means is we can put this in. We just need to take 750, multiply it by 9.8, and then multiply it by 6. And what you'll get here is 4.41 times 10 to the 4 pascals, which again is the SI unit of pressure. Right? Or alternatively, if you want to deal with a slightly smaller number, you can put this in terms of kilopascals, 44.1 kilopascals. And then you're all set and ready to go. Again, the trick here is to deal with the fact that you can combine like quantities together to deal with differences as opposed to explicit heights. And you can eliminate terms that are the same from both sides. Now, with that being said, do a quick sanity check here. Pressure should always be a little higher when you're lower due to gravity than when you're at the top. Therefore, our difference in pressure here between the bottom and the top should